Hello there, I'm Maurizio Martignano from Spazio IT, and I'm going to show you a small example of applying homomorphic encryption to medical data. In order to do that, we take some example data using the rapid core case report form used by the World Health Organization to handle COVID-19 information. This form consists of three modules. We just concentrate on the second one, module 2, and we only consider the small section, the vital signs. So basically, our data consists of, first of all, the ECRF ID, which is basically the row ID, then the participant ID, which is a patient ID, then we have the follow-up date, that is when the vitals were taken, and then we have the vitals, the temperature, the heart rate, the respiratory rate, the systolic blood pressure, the diastolic blood pressure, if there was the dehydration or not, and then the capillary refill time, if that was less than 2 seconds or not, then the oxygen saturation, how the oxygen saturation was measured, and then the APVU value and the Glasgow Coma Score. We're talking about a small data set of 40 lines, 40 records, and consisting of small integers basically and strings. On this very small data set, we are going to apply exactly the same application, and basically we're going to do a table search looking for rows that satisfy particular conditions. And we're using the same application but developed with the two different libraries. Okay, that is one with ZAMA TFHE and the other one with IBM HELIB. Which version of them? So basically the last one's available, and for ZAMA TFHE-RS is 024, and for IBM HELIB is, I don't remember, it's version 222. So now we're going to run these more applications. Close the browser and go into the proper place. This is a Rust application. This is a C++ 17 application, and so here we do cargo run -- release, and here we just run the application. Like this. In both cases, we can see that the encryption process is started. Here we have that each row is printed as soon as it is encrypted, and you can see that IBM HELIB is kind of faster than ZAMA TFHE-RS. This depends on how the encryption is done, how the keys are developed. Now the funny thing is that the keys used by HELIB are bigger, stronger, and the encryption is stronger in the case of HELIB, then it should be faster. Sorry, it should be slower encryption because it requires lots of performances, computational power. On the contrary, it is ZAMA TFHE, which is not so fast, even if the keys are not that big. Okay, so we start entering the search. We look for rows that have, say, the respiratory less than, say, 12, and the systolic pressure higher than 120. 20, and we are applying the same condition also to the other application, which using the other kind of encryption. So number again, number respiratory less than 12 and again the systolic blood pressure bigger than 120. We say that we're done both. So the search is on homomorphic values, that is on encrypted values, starts in both applications. Here the searches are running. The timing of the search is different. In this case, ZAMA TFHE seems to be faster, and we'll get soon the results of the search. So the number of rows that satisfy both conditions. There they were basically respiratory rate less than 12 and systolic blood pressure higher than 120. Here says one row satisfies the condition, and let's see here when it finishes if we have the same result. Okay, so if we go to the data set and we check for the value, of course we'll find that actually the rows that satisfy condition are actually only one, so it's okay. So what we can say that basically the performances are not very fast, and different libraries perform in different ways in different phases of the process. During the encryption, it seems that HELIB is faster than ZAMA. During the comparison, ZAMA is faster than HELIB, and we're talking about say performances which are order of magnitude slower than the actual performances when no encryption is used. But things are evolving, and with the passing of the years and the months, we can see that even without changing the hardware or the computational power of the machines, just using newer version of the libraries, we see improvements in performances. So this is something to be look carefully and see if we have something which is, say, good enough to be used in actual applications. And this is it. Here ends my presentation. Thank you.